For studying rough weather, the National Weather Center in Norman, Oklahoma is at the center of the action. Inside, researchers are working on what is called the Hazardous Weather Testbed. Participants work with the latest computer models and cutting-edge forecasting techniques.
It's about bringing practitioners or operational forecasters together with researchers and computer modelers, a very broad community, and bringing them all together to focus on the next generation of weather prediction.
Typical workdays start after noon. It's taken all morning for the sun to heat the atmosphere. Warm air rises, and rising air mixes it up. That churning air is what provokes severe weather, and that's what these experts are studying. They're also getting ready for the future. A brand new NOAA weather satellite is on the horizon. Once launched, it will take its place in space and offer a wealth of major new capabilities.
GOES-R is going to be unbelievably helpful, whether it be lightning data or cloud. We're going to have so many more different channels in terms of visible or infrared that will help us in terms of forecasting and figuring out where that severe weather is going to happen.
GOES-R may be the latest in a long line of satellites, but its new capabilities will be more than just a tune-up.
So it's going to be like putting on glasses compared to what we have today. So this is going to be a great improvement to our methods right now.
Rough weather used to be the great unknown, something always over the horizon and capable of arrival without warning. But times are changing, and with hands-on training like that of the Hazardous Weather Testbed and new technology like GOES-R, forecasting will continue to develop into one of the only disciplines that can actually foretell the future.
South Oklahoma City, it'd be big hail and lightning would be my biggest concern.
After all, knowing tomorrow's weather profoundly affects decisions today.
Say you've been observing Earth's weather using GOES satellites for the past 40 years, and suddenly you realize you need to launch another satellite to keep doing it because it's really important. Naturally, you might think to yourself, great, let's just box up parts from the previous satellites, launch them into space, and let them do their thing. Unfortunately, that's just not how it works. Scientists and engineers are always looking for better ways to improve the weather forecast, and for them, images like this from decades-old satellites just aren't quite up to snuff. Thankfully, scientists and engineers have been busy working with meteorologists to improve things, so they have an idea of what data is needed next. That way, when they launch a new satellite, they're adding to what they've learned before, which means even better weather forecasts for the rest of us. So, when you build a satellite in NOAA's new GOES series, called GOES-R, it naturally sets off a flurry of activity. Because they always want to improve things, engineers might change the satellite platform, upgrade all the instruments, and, because it's meant to improve the forecast, add something totally new that's never been done before, like a new lightning mapper. After months of constructive debates, and probably more than a few late nights, they'll finally come to an agreement. Once everything's been approved, the engineers get to design and put the satellite together. However, even though they've built GOES satellites before, it's not just a matter of pulling out the old designs and bolting everything together. Because there's new science to be done, things have to be redesigned, modified, upgraded, built, tested, retested, tested some more, and finally delivered, so that at the end of the day, it all fits neatly atop a giant rocket. Once all that's finished, the satellite launches into space, the scientists and engineers celebrate, and lots of new data starts coming in that improves the weather forecasts for us here on Earth.
Hi, I'm John Dorelli. I'm a space scientist at NASA's Goddard Space Flight Center. I'd like to tell you a little bit about NASA's MMS mission. MMS was designed to study a phenomenon known as magnetic reconnection, which is kind of a magnetic explosion in space. You can think of Earth as a giant bar magnet with magnetic lines of force emanating out into space in a dipole pattern. Under just the right conditions, energy in this magnetic field is explosively converted into plasma energy, creating spectacular space weather phenomena like the aurora and magnetic storms. To catch these explosions in action, the MMS orbits were designed in 2 phases, a dayside phase and a nightside phase. MMS is actually 4 identical spacecraft flying in a geometrical formation known as a tetrahedron. Scientists hope to catch the magnetic explosions somewhere inside this tetrahedron. At closest approach to Earth, the tetrahedron is highly stretched and not suitable for capturing the magnetic explosions. But by the time we get out to 76,000 kilometers, MMS will be a nearly perfect formation, with the 4 spacecraft separated by only 10 kilometers. The Sun is constantly blowing out its atmosphere into space, and this solar wind meets Earth's magnetic field at the magnetopause. Here, at the magnetopause, scientists expect to catch magnetic reconnection in action. So the apogee of the orbit is designed so that the tetrahedron cuts across the boundary twice per orbit, while in perfect formation. As it crosses the magnetopause, MMS will take high-speed snapshots of the magnetic explosions as they unfold.